근데 마이크가 이 마이크가 들어오네. 오, you're live. 아.
아 이거? 아
렉은 안 되네. 여기 와이파이가 잘 안 돼. 이 정도면 KNU로 바꿔도 돼요?
네네네. 그럼 아마 근데 끊어질 텐데.
근데 다시 연결되지 않을까요?
이게 목소리가 잘 들어가야 하는데.
곱셈 충전기 가지러 갈 때 뻘을 하고 가지고 오는데
이 댓글은 뭐? 댓글 나는 게.
떠났죠?
앞에도 했었는데 이거 촬영을 대박.
那这个3是什么？3是因为周六的话，他周五对，这个是现在的。
그래서
让我们去一在旁边嘛，然后就整个几个就是特别那种，然后也看我看我想的，我说什么？我说什么？我说的那些，我在想，我觉得是当现就是我一个人做这个觉得好看，我觉得其实我觉得这样子。
해결.
네. 지금 나가고 있습니다. 해결하기 기쁜 공연이 라이브로 송출되고 있습니다.
이거 카메라 어디 있는 거예요?
여기 너무 잘 나오고 있어요. 지금 나오지 않는데 보면은
틀어놔가지고
나 오케이? 콜셋?
지금 시작했어요. 미리 그냥 확인하다가
아니
시작했거든요.
30분이 남았는데.
근데 끄면은
끝이야 이제 못 돌려? 또 혹시 모르니까. 이거
그러니까 링크를 다시 해놔야 돼가지고
앞에 캡을 막아놓은 건지. 뭐 그래도 되는. 뭐 내가 그러지?
지금 나.
감사합니다. 진짜 감사해요. 근데 나 진짜
또뭐 했다고?
이거 제가 하는 거 카메라 해주셔서 아 이렇게 해서 빗자 놓으시려고요?
왜냐면 2시잖아요.
아, 네.
빨리 이거 끄면 그게 날라.
그쵸.
화면 공유 안 돼 이거?
그러니까 이거를 이렇게 해서
아
뭐라고 해야 될까요?
14시 관련 예정
14시부터
14시 관련 시작 예정입니다. 입장.
아니면 저기다가 끼워놓을까요?
아 근데 그 사람이 지금 그거 주문하시면 이거 캡으로 막을까 해서. 그래서 아무것도 안 해도 연결돼 있어.
이장 교수님이 계속 우리랑 같이 얘기해야 되니까 못 드셨어요? 교수 샐러드 만들어요. 샐러드 만드셨어요? 힘이 나셔야 되거든요. 학생만 이렇게 궁금하게 선생님 내일 수업에 저는 안 너무
빡치는 글씨체.
엔점 어떻게 하겠습니다. 몇 마디 마칠 필요.
성적이 있다. 학생 올 때 가지고 가요. 지금 즐겁다. 아, 네네네.
저는 계속 수고가 많으시네요. 제가 저번에 참석할 때 이게 임세자를 참석했으니까 어제는 제가 참석 못한다고 이렇게 참석했거든요.
사실은 저는 말씀할 필요가 없는데 왜냐면 서면서 수 있어서 그것 때문에 저는
네, 간 김에 이제 했는데
그럼 이거 여기 끝나면 저거 다시 원래 바로
다른 거 들고 가야 돼.
근데 그때는
그럼 홍련 보이는 거 가져갈까요? 어를 가져갈까? 아니 이거 가져가는 게 샵 있어요. 이거 너무 찌랄 거.
아니 그냥 메모지만.
알겠어.
네.
가져올게요.
네. 돈도.
내가 뭐 큰 기능을 받으면
네, 뭔가 이제 네.
꼭 둘러봤다.
지금 안 해요.
운동기가 다른 게 아닐까요? 이거는 끼우는 거예요.
아니 뭐가 바보.
언제 이거를 끼우는 거예요?
안 그래도 여기라서 소리가 낼게 없어요.
하고 내가 소유 느낌이 흐르는 거 있어요. 이거 시간에 이문학 시간관이 115에 있었거든요. 그래서 혹시 어디 계시나고 여쭤보려고 했는데.
수영생 연구하는
강의라고 해요. 강의라고 네, 지금 무슨 강의냐고 계시나요?
지워져.
아니다. 오늘 오늘
이게 영어.
내려가는데 지금 하고 있는 거가 현실에 그
지금 대학원동 대기로 여기 밑에 여기 밑에
대학원동
예,
대기로요?
네.
안녕하세요. 이거 장관이 같습니다. 네. 지금 커피 드시고 싶어요.
안녕하세요.
이렇게 보면서 재현 대표님이 칭찬하더라. 정인태는 잘 되는 사람이라고 얘기하시더라고요.
I assume that person is just somewhere down in the hall. Oh, right.
눈이 안 좋으니 테레비 가까이
근데 이 방향이 낫다. 여기 안 나오게.
지금 몰랐어요.
여기 당황하고 있어요. 지나가면 가면 독일 사람인데 그냥 여행장이고 진짜 정도 못하고 영어를 가도 돼요. 좀 힘들지 않아? 5월에는 나올 수 있어요.
엄청 안 좋을 때 애들 앞에 진짜 쑤셔서 간지
오늘 밤새더라고. 근데 이거 뗄 수 있어. 빼고 집에 가도 그냥 답답하면 병원 안 가서 모르겠어. 그래서 그랬는데 내 느낌 자는 이게 왜 사람이 발목이 이렇게 서면 이렇게 딱 잡힌 느낌이 있어요. 진짜 신기해요 이게. 흔들거리는 느낌.
우리 진짜 뭔가가
가난하고 이렇게.
그래서 인내가
영혼이 좀
회복이 안 된다고. 맞아, 인내는 되게
무섭다.
그 인내가 다시 듣는 느낌이 나는데 그 주변 근육에서 되게 인내를 하게 인내 자체가 원감이고 맞는 계속 늘어진다. 하열 불안증이 심한 사람도 맨날 뭔가 완전히 안 되는데 같이 같이 보관에만 그래도 그거 아닌 거야. 내놓는 짜. 아 누가 산 사람이 많아. 그런 게 있으면은 오빠가 강아지도 그 거칠 이렇게 크게 나 혹시 그럴 때 필요해. 근데 잘 보는 살짝 있었어. 죽은 줄 알았어. 그렇게 늘어나 자기라서. 그래서 그냥 이거 다 그 똑같은 얘기야. 몸이 그거려서 그거 이거 하는 게 나아. 나 진짜 진짜 몇 개월을 계속 그걸 하는 거야. 나 너무
진짜
정말 미치고 잘 넘어지. 근데 난 그게 힘들지가 내가 안 가봐.
꽤 많이 넘었어. 늘어나 있었나 싶은데. 조심해야 계단만 가도 트라우마처럼 죽고 다니고 너무 시겁하고
남자가 올라가지 마. 성비가 달라.
아 진짜?
원래는 안 돌아오네.
나는 처음에 쌤 신기했어. 처음에 이렇게 말했잖아요. 저병까지 꼭 할래. 난 그런 걸 항상 태어나서 처음 난 살면서 저병이라는 단어를 생각해 본 적도 없어. 이분 저병을 하실 생각이었어. 진짜 쌤은 근데 약간 차근차근 좀 열심히 하실 생각이었어. 제일 좋아요.
우리 강아지 좀 많이.
제일 좋은 거는 지금은 진짜 내가 자연스럽게 설명하고 있으면은 미디어 거 우리 엄마가 그거 안 된다.
그 동생 제가 이름 찾아봤지. 강사 이름 여기 있어. 근데 76번. 뭔가 난 잘 가르친다는 생각이 좀 들었거든. 진짜 약간 교육자처럼 느낌이 있어서 교육받았네. 다른 사람들 이렇게 더
없어가지고 딸딸이 양도에 이런 실제 가르치는 사람들은
왜 그렇게서 쟁쟁한 사람들
너무 힘든데
막 돌린다.
내 얘기니까 아니 원래 내가
혼자 가는 거야. 같이 보내는 거야.
먼저 가니까
Bachelor in Germany and then Master in France. And then I started my Master in German, Master here. But at least every time I moved on to
이자가 공감했다가
I think I'll be okay. I think the back rows will hear me. I'm very loud. I will project. I will fill the room. Ah, you're streaming as well. Okay, if you want to wear a microphone, I will, yeah. Ah, I'll forget. You haven't got a, you know. Oh, somebody I want to walk around. I want to follow them around. How many people are watching? Somebody who's streaming. Yeah, I'd like to have a group working with teams. Yeah, I'd quite like to walk around amongst them. So how many people are streaming this? Are you? Okay, let's just, you haven't got a keyboard microphone. I don't want to walk around. Okay. Good. Can I move the table? Yeah. Hi. So I can move the table. I want to put this to islands. So join two tables together. I want them to sit facing each other, working together. So for example, is it possible to move this one? Oh, they're joined. They're joined. Okay, they have to sit facing this way and work together. They can, yeah, but they can do that after I start. I'll get them to join the class. To work as a team. Yeah. 1, 2, 3, 4, 5, 6, 7. Perfect. Nice. Good. I was thinking I don't mind having you in a group, but 4 is good. But I've no more than 7 groups. Because I only have 7 dice.
저쪽에 여기 3개 테이블을 일단 아니 하나만 비우면 될 것 같아요. 뒤에 8개가 있으니까 네, 여기 테이블을 비워주세요. 여기 테이블을 주시고 이렇게 마주보고 아니 여기 주에는 찍었네요. 네. 그러니까 반드시 8명이 들어가고 여기 테이블만 비우고 마주보고 적당히 앉으시면 여기 또
그냥 소리
그룹을 저희 애들이 많아서
Ten times in a row and having to every time. Now, we've done this under control conditions with multiple cameras that won't cut away, and it's a genuine coin that heads on one side, the tails on the other. But I want you to watch this and try to work out how it can be possible. The key to understanding this is the key to understanding the system. 10 heads in a row. What the same way. And then toss a coin fairly 10 times in a row and have it come up heads every time. Now, we've done this under control conditions with multiple. I still don't have them. Really, this, force them to listen. Yeah. Cameras that won't cut away, and it's a genuine coin with heads on one side and tails on the other. And I want you to watch this and try to work out how it can be possible, because the key to understanding this is the key to understanding the system. That is to toss a coin fairly 10 times in a row and have it come up heads every time. Now, we've done this under control conditions with multiple cameras. Well, seriously, I don't want to make mistakes. I want to be told, I'm not joking, I want to be told about any mistakes. It's not my specialist area. So, yeah. I was going to go to the benches and I won't be. So I've got 2 hours. But actually, my opinion, like an hour 40.
아, 네. 아,
이제 녹차 시작하겠습니다. 준비 시간도 필요하신데.
Hello everyone, and welcome to this workshop. So it's such a great honor to have Professor Gabriel Egan with us today. So as many of you know, he is an expert of Shakespeare from the Montfort University, and he is one of the main editors of New Books for Shakespeare, which is a modern and detailed collection of Shakespeare's plays. And in addition, he has did many research projects by using different types of digital methods. So in this workshop, he will going to teach us how to use statistics to better understand the text, such as play and books. I'm confident that it will be helpful for us to understand how we can use the digital way of techniques with the text. Okay, so please join me in giving a warm welcome to Professor Gabriel Egan.
I'm going to project. I'm just going to talk to you. Pigeon, can I check backward? How's the sound? Loud enough? Perfect. Good. So I've got you for up to 2 hours. I'm going to take not a full 2 hours, maybe an hour and 40 minutes. And we will take a break halfway for about 15 minutes. We call it a comfort break in England. You can go to the toilet, get a drink, whatever. I'm not teaching you here anything that is my specialism. I'm very much outside of my own specialism. The one thing that's certainty. Yes, I'm definitely an expert on Shakespeare. I am not an expert on statistics. What I wanted to share with you are some ideas about how those of us who are trying to be expert in literature, language, can use numbers responsibly. That is, use numbers correctly. Because my feeling is that our intuitions are common sense about probability. And that's my key topic today, probability, likelihood. Our intuitions can mislead us. We can easily make mistakes. Where I'm going to hopefully take us all is a very few examples of some of the techniques for applying mathematical ideas to the things we find in language. And where I'm going to end up, and this may make sense to some of you, maybe not to others, I want to talk about the idea that language is a stochastic process, that it's a process that combines randomness with order, which is a very hard idea to accept. So I want to start with a demonstration of randomness that is also orderly. And it's not my demonstration, it's a man called Devon Brown. I'm going to play you on these screens a video of something Devon Brown did. I want you to watch and listen and discuss in your groups how he did it. Okay, he does something surprising. I want to know how he did it. Now, it may be that somebody will already know how he did it. We call him in England a magician. He's a performer who does things that look impossible, but they're not. But it's not obvious how he achieved what he achieved. So I want you to, in your groups, discuss how it was done. But if you know how it was done, please don't spoil it for your group. If you know for sure, if you think you're certain how it was done, keep quiet. Let the other people think about how it might have been done. Okay, here's what he's going to do. I'll play the video.
Show you something now which is impossible in exactly the same way, and that is to toss a coin fairly 10 times in a row and have it come up heads every time. Now, we fill this under control conditions with Montfort, and that is to toss a coin fairly 10 times in a row and have it come up heads every time.
Look there, that's the premise. He's going to show us tossing a coin, flipping. I've got, he's going to take a coin, flip it, and come up heads every time. That's what he's going to show us. I want you to think about how it happens.
Now, we film this under control conditions with multiple cameras that won't cut away, and it's a genuine coin with heads on one side and tails on the other. But I want you to watch this and try and work out how it can be possible, because the key to understanding this is the key to understanding the system. 10 heads in a row. Watch. 1, that's heads. 2, that's heads. 3, heads. 'Heads, that is 4. 'Heads, 5. 6. 1 more again, then I'll stop. 7. 3 more. 8. 9 heads. Last one. 10 heads in a row. Thank you very much indeed.
Okay. That's what he achieved. 2 minutes in your groups talking about how he did that. Is it clear why it's difficult? Why what he did is hard to achieve? Yeah. Okay. You've seen You've seen coins being tossed. You're familiar with that? Yeah. Okay, so discussion, how it was done. Because we've got any coins, have we? We don't have coins anymore. Everyone's got cards. Yeah. I forgot I wanted to ask about But they all have pens and pencils. They're likely to have. Yes, we are. Each table comes with one idea. One unit comes with best shared idea. I want each table to come with one suggestion for how it's done. I want to hear the table of best one idea. So give one more minute.
Yeah, one side. Yeah, one side.
Okay, 1 minute. 1 minute to go. And I'll take care of the ideas. Make sure you put an answer, at least one answer per nation. Okay, let's have the answers. Starting with, right, stop. I want to hear the answers. I want to write down the answers. Well, if I think they're good answers. Back to me now. Attention. Have you chosen your answer? I want one theory. This table. Why now? I want to hear this table's theory. What is your suggestion about how he did it? Over here. Shh. I want you to hear their answer. Okay? Your discussion ceases. Your answer. What? How was it done?
We just tossed the five.
I want a short answer. How was it done?
Yeah, we all have the.
No. How was it done?
We just tossed it like a movie theater.
Like a movie theatre. What does that mean?
I'm in the movie, like a movie. I'm in the screen you show,
Yeah.
but I didn't watch it. We didn't watch it carefully.
I want to know how he did it. What do you think of your theory?
We think the coin has two sides.
Thank you. The coin has two sides. Did any other group come up with that theory? Yeah, okay. So one theory is coin has, this thing wobbles, two heads. Yeah, coin has two heads. So he cheated. Yeah. Okay, what's this group table's theory?
We came up with that. There is no particular reason or trick. It just naturally happens.
It just naturally happens. It was just chance. It was just, okay, that's a theory, here's a theory. It was just chance. Good. Do you have a different theory?
Reason the foreign one side is more heavier and he used some special skill.
Did you hear that?
Yeah.
This was very murmuring while they were talking. The answer was, do you think the coin is biased?
Yep.
The coin, yeah. The coin is heavier, so it's naturally going to fall on one side, so it's a biased coin. The cheating coin, yeah. Biased coin. I like all these ideas so far. Did you have an idea? Well, yeah, I think I let you have two ideas. Then ask me. Go on, two theories.
One of the ideas is the multiple takes
Multiple takes.
and shows the best.
Multiple takes. And then edited or chose, yeah, edited for best one. Okay, that's one theory. I'm letting you have two theories. What's the other one? Oh, another coin has two heads. Yeah. And the last table, unless the professors at the back have a theory.
Same idea, particular thing.
Which one?
First one.
The first one? Oh, fourth one.
Yeah.
So 2 votes for that one. Shall I reveal the answer? Well, let's think about. First of all, no, he didn't cheat. It's not a two-headed coin. Okay. It was just chance. How unlikely is it that it was just chance? Does anybody know how to calculate the probability? 2 to the power of 10. Well, it's 1 over. Are we all clear what's being said here? It's a half, the chance of getting one head, multiplied, I hope you use that symbol, by a half, and so on. Let me know what that comes out as, all the way along to
1003.
yeah, of course it is, yeah, 2 to the power of 10 is what that, yeah. Yeah, so it's 1 over 1024. That's a small number, isn't it? So that's, I'll do it in decimals if you don't mind, 1024. Yeah, that is a small number. 0.000, so 3 zeros.
Oh my god.
Small number. It's basically 1 in 1,000. If that was a 1 there, it'd be 1 in 1,000. It's just slightly under 1 in 1,000. Good. So, yeah, maybe it's just chance. They just got really, really lucky. A 1 in 1,000 chance came up. It's a biased coin. Well, I can't prove this, but no, it isn't. He didn't cheat. So it's not that one. It's not that one. In fact, it's both of the remaining answers. They're both true. It is just chance, and he did it many, many times. He did it, it took a week of filming 12 hours a day and going away 980 takes. He did it until the result came up, and then showed us only the result that gave him what he wanted to show, the extremely unlikely event. What moral do we draw from this? I'll tell you in case it hasn't occurred to you. very unlikely things can happen, will happen, must happen if you wait long enough. If you're prepared to spend time, you can trade time for unlikeliness. Do you have a lottery, a national lottery in this country?
Right.
Yeah. Every week, somebody, well, if your lottery is like our lottery, every week, somebody wins the lottery at an extremely low probability of winning. And they have to. That's really peculiar. Something very, very unlikely must happen. That's a paradox. And what I want to show today is try to make sense of that paradox, that the extremely unlikely things have to happen because of the conditions, in this case, the way he edited. Well done, by the way, for figuring that out. But they have to happen because he gave himself the time for them to happen. To see a way to get from probability, uncertainty, unlikeliness to certainty. That's the journey I wanted to take, is from uncertainty or unlikeliness. Unlikeliness. Sorry, I put forward as well. To certainty. I want us to see how we get there, because the reason I want us to do this, our human intuition, our common sense for likelihood, probability, is poor. It's very weak. We need the culture of mathematics to correctly predict events being likely to happen or not likely to happen. Maybe you've seen this already. Haven't you got enough people in the room? What do you think is the likelihood that two people in this room share a birthday, born on the same day? Does that seem likely or unlikely? What should we find out? We'll ask each person to say their birthday, and we'll stop when somebody hears their own birthday.
September 18th.
November 21st. 2/24.
Your birthday? Yeah. Okay, but then listen out for your own one.
January 9th.
January 21, yeah. January the 10th, okay. It may not happen, go ahead.
November 13th.
November 13th.
February 24th.
June 24th.
January 27th.
June 11th.
May 7th.
Do stop if you hear your date.
August 5th.
August? Yep.
October 16th. August 22nd.
August 22, yeah.
June 21st.
July 31st. March 28th.
December 20th.
December 23, yeah.
October 14th.
February 1st.
January 23rd.
April 7th.
April 7th.
February 24? 24.
I didn't know, but I gathered it would be true. In this size of a group, it's usually true. Our common sense about that likelihood is completely wrong. In fact, for any group of this size, it's very likely that two people will share a birthday. I can demonstrate that to you, but I want you just to notice it, that it's a good guess it's going to happen. I want you to generate some unlikelihoods, some randomness, using dice. So it's one pair per team. So you shake, you get a red and a blue number. So you shake, keep them in the box. A lot of you. Hang on. On your paper, you have a chance to record your dice rolls, okay? I want to see a record of what your dice have up as. So take your graph paper. Somebody in the group needs to record. I want you to make a chart, a picture of what you get. I'm going to use blue if you can leave red, doesn't cost very much. So I want you to record on this side. I want red, blue. This refers to the colour of the die that you've got. For red, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And for blue, you can get a 1, a 2, a 3, a 4, 5, or 6. So when you roll, I've got red 2, blue 5. So I do this. And then I do it again. I've got red 3, blue 6. Now what's going to happen is when you get a number, I'll do it one more time. Red 3, blue 5. So I get a chart, grow. Well, we're leaping ahead. I want you to do that separately for the 2 die on this side of the room. You will do something slightly different. You're going to add the 2 numbers together. So instead of 1, 2, 3, 4, 5, 6, what are the possible outcomes if you add the 2 numbers together? What's the lowest sum you could get? 2. 1 and 1. So you won't have a 1 here, you just have a 2. 3, 4, 5. What's the largest you could get? Yeah. 7, 8, 9, 10. I want to see the sum. So each time you roll, 5 and 3 gives me an 8. Okay. Another 5 and 3. Another 8, surprisingly. And 5 and 5 gives me 10. Okay? So that's what you're doing. Okay? I shall be coming round to make sure you're doing what I've asked, and we're going to watch these shapes as they develop. So 5 minutes to 10, depending how quickly you can do this. So you should roll.
이거 다른 걸로 하면 다른 걸로
줄이니까 이거.
아 여기는 알고
편하게 하시면 여기가 필요하시죠.
위에다
드디어. 다른 사람은
랜덤 느낌.
The only table that doesn't look good. The rest look perfect. I will take 2 more minutes. A little bit more to take 2 more minutes.
도장을 하고
그래서 actually next, let us predict. I want you to predict the results. I'm just going to check the back on. I want people to say what they think the other side has got. So people on this side, does anybody care to predict? Can I take your sheet of paper? Can you have yours? Can you predict what we will see from this side? What do you expect them to achieve? They were recording 1, 2, 3, 4, 5, 6 for red, 1, 2, 3, 4, 5, 6 for blue, separately. 2 tables, 2 charts. What would you expect to see over here?
I suppose.
No, we had a mime over here. Not a verbal answer for the demonstration. But you're going to give us a verbal version, yeah.
I suppose there's no outcome of red is one and the blue is also one.
Attention. Yeah, say it again, it's a great answer.
I suppose the red is one and at the same time the blue is one is the outcome is not coming. I guess because it's not coming.
Well, I don't compare to yours. I want to have a version of your rhyme. What's put that into words?
In general, the numbers for blue are relatively same, and red and blue are the same.
So red and blue are the same. And what about 1, 2, 3, 4, 5, and 6?
Also relatively even.
So you expect something like this: 2, 3, 4, 5, 6. Something like that. Is that what you're saying?
Yeah.
Yeah. Can you see why she's predicting that? Each die, singular dice, 1, 2, 3, 4, 5, 6 is equally likely. If they're fair dice, I should have said I've given you fair, unbiased dice. I put it down, I don't know what I did with it. Yes. Well, not exactly, sort of. But not exactly, not because they did it wrongly. But not. Who said what again? Chance, yes. Yes, how many throws do you think they managed? Maybe 50 at that time? Can I see yours? Now, they made theirs more carefully, much more tidily, thank you. Beautifully done. Because they kept, unlike over here, they kept the X at the same height. So yes, that's a, yeah. Thank you. What about this team? Also, quite untidy, but we're seeing roughly the same idea. There's no obvious pattern. That's the key point. There's no distinct pattern. Now, over here, don't let them know what you got. I want somebody over here to predict what that side got. I can see it being drawn, right? Some people might have specialist knowledge. I want somebody who doesn't think. Go ahead.
It must be have a bell mounted.
Well, the fact that you've used the word bell tells me you know this is correct, I think. Yes. I want, yeah, the prediction. Anybody else want to make a different prediction, or you all like that prediction? You all like that prediction? That was a bell. That was what you were also drawing, wasn't it?
I could tell you the reason.
You want to give us the reason? Yeah. Is that what you're predicting? A bulge in the middle. Yeah. What's the reason?
It's more likely for you to make a 7 or an 8 or the 6 in the middle if you try to them.
Why is it more likely to make a 7 or an 8 or 16?
Because the numbers add up more to this.
Let's have a look what they got. Is that what you? Very good. Nicely done. Yeah. A bulge in the middle. Have you got a bulge in the middle? Yeah, they've also got a bulge in the middle. And finally over here, same thing. Yeah, bulge in the middle. Let's have another version of that. That's the correct explanation. I want it absolutely clearly expressed. Why do we get a bulge in? Why should we get this shape? Why? Like also get just 100% of the way.
So if you make so together 2, you only have only one pair that can make a 2.
Yeah, which is 1 plus 1.
You also have
The only way to make a 2.
the only way to make a 6, 12 is also just 6 plus 6 or 1 pair.
It's the only way to make a 12.
And as you as you get closer to the middle, you get more and more chances to make. You get more and more pairs that you make a 6, 7, and 8.
Well, let's take a 7. How many ways are there to make a 7? 1, 6, 8, 2 plus 5, 3 plus 4, whoops, 3 plus 4 plus 3, 4, 5 plus 2. Yeah, there are more ways to make the numbers in the middle. 7, many more ways than there are. And as you get towards the edges, there are fewer ways, so they come up less often. So that well, let's just demonstrate that on the screen here. If that's true, the question to be asked is why we didn't get a perfect result. Why did we only see, well, we didn't get absolutely even settings over on this side. We didn't get the same number as 1s, as 2s, as 3s, as 4s, as 5s, as 6s. So we didn't get a perfect bell curve on this side. I'm going to show you a small bit of Python code that will allow us to just simulate doing, say, 50, 100 of those of the dice. So that's what happens randomly if we throw the dice 100 times. We get red face 1, red face 2, red face 3, 4, 5, 6. Quite uneven amounts. Same for blue. And also, well, there's a pattern to them combined, but it's not quite the smooth bell curve we would want. The data is ragged. The data is uneven. Because what? Why is it not smooth? Why don't we get a perfect shape? What's that?
The set is finite.
Okay, that's a complex answer. I was going for a simple answer. What do we need to do to get more near to the ideal? Try more. Yeah, that's 100 thirds. But that was give me a large number of thirds. Can we go something between thirds? Something between 100 and 100,000? Give me another. 10,000. Here's with 10,000 thirds.
Wow.
It'll be a lot more even. Yeah. And then someone said 100,000. Let's try that. These numbers are random. Well, you're not seeing your projectors. Some screens aren't coming on. All screens are not coming on. They're all gone. What's coming and going? If the red button turns it on or off, aren't you in danger of putting some on and some off? I should say, sorry, in these charts, it's all been rotated 90 degrees. I'm not a good enough programmer to do anything. write the program to produce it the other way around. But the coding is easy, definitely this way. So you've got to imagine these pictures turn 90 degrees. That was 100,000. Let's try it again with a million. Takes a bit longer. And if things don't get any better, let's try 10 million. So take quite a bit longer. The data isn't perfect because also 10, 11, 12, there's numbers being slightly wider than, yeah, but then they are, yeah. Yeah, it's going to be nearly perfect. In fact, we can't see a difference in the top two. You predicted, some of you predicted that outcome. The outcome of a million or 10 million rolls of the dice is completely predictable. And the outcome of one is completely unpredictable. That's paradoxical, but it's the nature of large numbers. And each time we do it, we're going to get the same result. I'm going to do it again for the 10 million. Every single roll, not every single roll, but many of the rolls in the second simulation will be different from the first. But the outcome is 10 million. The outcome is indistinguishable. That is, the second go, do 10 million again. Did I do 10 million correctly? Should be 7 noughts, is that right? Yeah, 1 second. Yeah. It's going to take a while, but the outcome will be a completely different set of rolls, of which the results are nonetheless the same. In fact, that's what proves that dice are fair. You can't tell if dice are fair for one roll, but you can for a million rolls by looking at the overall averages. Yeah, the answer. It's the same. So let's think about, I can put it outside, let's screen 12 again, now go to read my own notes. Your intuitions about that, by the way, were very good. I think some people who spoke up actually knew where they were going with this, and perhaps some people who didn't say anything were surprised by the results. But people often use intuition, common sense, to make predictions about things, and sometimes the results are important and wrong. There's a legal case, there's two I want to talk about, but the one, there's a famous case in England where statistics were used in a court trial. A woman in her 30s had the misfortune to have one of her children die as a baby by what we call sudden infant death syndrome, or sometimes called Cox death. It just happened. Babies stop breathing and they die. And the country's leading expert, Professor Meadows, said that the chance of this happening was 1 in 80,000. If you have 80,000 babies, on average, one will just have this happen to them. For no explainable reason. We don't know why it happens. It's called sudden infant. It's actually death. I think it's called something death syndrome. SIDS, yeah, syndrome. I can't remember if that's how you spell syndrome. It's not. 1,80,000. This woman had it happen to her. She had another baby, and it happened again. So Roy Meadows, our leading paediatrician, as we call them, the country's greatest, in fact, he was Sir Roy Meadows, because he had a knight for his genius. He said, that's the chance of one happening. She's had 2 happen. Where do you think I'm going with this? What did he conclude? Do you think? Yeah. So it's 1 over 1,000 times the same. So it's 1 over 180,000, so it's 1 over 80,000 squared. 80 squared. It comes out as I also do it as a decimal. He told the jury, well, that is the likelihood of a woman having 2 of her babies die of sudden infant death syndrome. And he said that number was so small, it couldn't have happened. She killed them. She must have killed them. And the jury agreed with him, sent her to jail. The Royal Society of Statisticians, a body in Britain that represents the profession, got involved. Anybody want to guess? Now, those who really know, try not to guess. Those 1 or 2 people know this, but those who don't know but might guess. The Royal Society of Statisticians saw a fatal flaw, fatal literally, for the babies, in this logic. What do you think they said was wrong with the advice given by Sir Roy Meadows? What was the mistake? I will let people who do think they don't need jump in if they want to have. What do you think is? Well, how have they gone wrong? If that's false, if that's misleading the jury.
I think it's not 0%. It could happen.
You didn't take account the entire population.
No, he did. He did. There's a single word I'm looking for, begins with I, that is not met by this case. Something that this example lacks. These are I. I'll give you 1 letter at a time until you get it. What does it not have? It doesn't have inference, both good guesses, but no. Independence. Yes. Doesn't have independence. If you've had 1 baby die for a reason that science cannot explain, we do not know why. By definition, we do not know why the baby died. We don't know. We know how often it happens to the general population, but we don't know why it happened to you. And therefore, we don't know if the variables are independent. It could be, we will discover that there's a genetic reason for this happening. It could be that there's something in the environment in one place. We don't know why it happens, but if you don't know why it happens, you don't know that they're independent. It could be that some people have a tendency, some women particularly might have a tendency, or men could come from either genome to this happening. And without independence, I'll fill that in. Without independence, that is, it may be that one of these numbers depends upon the other. It may be that if you've had one, you're much more likely to have a second one. The Royal Society of Statisticians pointed this out, and on appeal, as we call it, the case was overturned. After 4 years in prison, she was released. She never got over it. She died shortly afterwards herself. Because they're not independent, that was the fallacy. The Royal Society of Statisticians also said that what the jury should have been told was, it is very rare for a woman to kill her baby. It is extremely rare for a woman to kill 2. You must consider all other possibilities before you come to a conclusion of murder. This was 20 years ago, and everybody concluded that, okay, now, this wouldn't happen again. We now know this. We now know how to use statistics in law cases. However, there's a woman currently in jail. Anybody know the case of Lucy Letby? Is that news? Well, she's a nurse, and so she worked in a children's ward of a hospital, baby, or neonatal ward as we call it, and babies started dying. And they started dying on her shift when she was working. And the jury was convinced that she must have killed them because there were just too many dying on her shift in particular. This is, it's worth looking up. It's currently being considered she may be released. She's currently in jail for 8 murders. And it is the case, there are previous cases of nurses murdering babies. That's not really possible to happen. But she may be released on appeal because people who are experts in statistics have found similar problems with her, the evidence that convicted her. It was purely statistical. They have no other evidence against her. It was just that all the babies died, the 8 died on her shift. But other babies died too when she wasn't working. And judging how likely it is that she was the cause is much more tricky, much more difficult than we might assume. So what I want us to do in the second half, I'm going to take a break in a moment, is to look at just one example of a whole suite, as we call it, a whole range of tools that we can use when our intuition is not helping. A man called Thomas, I think Thomas Bayes, came up with a theorem, Bayes' theorem, possibly Bayes' theorem, I'm not sure, but his name was Bayes. He came up with a brilliant and simple piece of mathematics that will help us to overcome our intuitions and do some of this work reliably. I'm going to give you a scenario to think about during the break. Okay, I want you to do nothing more than think about it, how you would react. So I'll give you the scenario, and then we'll try to actually work out the real answer. So, it's a scary scenario, I'm afraid. Suppose there is a disease that affects 0.1% of the population. There's a disease that affects 0.1% of the entire population. And there's a test for the disease. And you've taken the test, or you have, or I have, and tested positive. Okay? The test gives a positive. I'll give you all this information properly in the second half, but just to give you a flavour of where we're going. The test will give a positive result in 99% of the cases where the patient has the disease. In 99% of cases where the patient has the disease, the test will be positive. And the test will give a positive in 5% of the cases where the patient does not have the disease. Do you think you have the disease? I said it again. The disease affects 0.1% of the population. There's a test for it. It's not a perfect test, it's an imperfect test. But the test will give a positive in 99% of cases where you really do have the disease. And it will give a positive in just 1% or 1 in 20 of the cases where the patient does not have the disease. How worried should you be? Just ponder that, because we'll have to figure out the right answer in the second half. It's exactly 3 o'clock. We will resume at 3:15, 3:15. Okay, 10-15 minutes. Yeah, come for a break. Swig of water. Yeah, so one is so disease
거의 진리였어요.
내가 나중에 컸었기 때문에 얼마나 무섭겠는데 한국에서 그렇게 하세요. 내가 컸었기 때문에
재밌을 것 같은데. 제가 생각했던 거랑 달라가지고 두 번째 시간에.
But you don't know because you don't have the customer might tell you that you have
그 답변 들었습니다. 네. 네, 알겠습니다. 네, 감사합니다.
그러니까 양성일 때는 내가 양성 확률 나왔을 검사가 59% 정도 같다. 검사를 했거든요. 근데 내가 양성일 때 얼마나 더 해야 돼?
내가 그
아니면 진짜 양면을
This is disease. This is anesthesia. I just don't know where to put the variables. It's too easy. You do it. What's in your pocket? What's in your pocket?
What's in your pocket? We're very curious about it.
Okay, honestly, yeah. Oh, that's like Indiana Jones.
Yeah. I love
What? Oh, my goodness. It is tough.
actual positive using rates.
What 0.1% or 0.0001. That's the general spread of the disease in the population.
시간 많이 걸리는 시간 어느 날 어느 날
내일 점심은 이 컨셉으로 같이
제가 야성을
한다면은 시즌 이번 쌤이 어느 순간 시간을 갖고 싶어 하시는지 그것도 맞는 여기에서 먹을 아직 아 그게 아직
지금 뭐 정말 뭐가 이해가 되면은 다 말해줄게요. 지금 우리가 하고 있는 거에서 셰익스피어가 에디터라는 거 지금 하고 있는 거 근데 그거는 나도 이렇게 나도 이제 뭐 그런 거를 다음에도 다른 여러 가지 그거는 제가 기억을 하고 있다가
그리고 만약에
지금 뭐 이것도 거의 이게 마무리 단계에 들어갔어요. 그래서 또 이게 우리가 이제 3년을 넘었기 때문에 참여하기 그러니까 지금 얘기하고 거의 들어가요. 저도 이제 생각을
다시 한번 해볼게요. 어떤 건
여기는 다 저기 있어.
아니 그거
너는 교실이라고.
주변에서 그 디지털 인문학 강의자들이 책 제작하고 있습니다. 그거를 그게 딱 맞으면
Others being very
Start again. Let's begin. So I'll give you the setup again, this time with some mathematical notation. So what I said was, there's a text, and there's a disease. And it works like this. The probability, start again. The disease affects 0.1% of the population. In any population of any large size, 0.1% of all the people in that group will have the disease. And there's a test for the disease, and you've tested positive. The test gives a positive in 99% of the cases where the patient has the disease. And the test gives a positive in 5% of the cases where the patient does not have the disease. How worried should you be? That is, how likely is it that you have the disease? This test, by the way, this question is often asked in Britain to doctors who are being trained, because even ones who have been trained usually get it wrong and tell their patients things that are not true. This is Bayes' theorem. Let me talk you through the notation. P stands for probability. And after a P comes brackets, and that's the probability of that thing. And the bar, the vertical line, means given that. So I'll read out how you say this aloud. The probability of A given B, that is, the probability that A is true if B is true, is the probability that B is true given that A is true, multiplied by the probability of A divided by the probability of B. That's Bayes' theorem. There's not time to prove why that's true, but I want you to understand the notation. I'll say it one more time. Probability of A given B is the probability of B given A. Times the probability of A, all divided by the probability of B. One more notation I want to use is the not. When I say probability of A given B, I could instead put a little apostrophe after the B and say not B. The probability of A if B is not true. So the apostrophe means not. So let's go to our question. Over here, I've got the probability of a person, any person, having the disease. The prior probability. That is, if we know nothing else, and we just know how much the disease has spread in the population, what is the probability that any person in particular will have it? I said it was 0.1%, which in a decimal is 0.001. Happy with that?
Yep.
That's the same as 1%. I also said that the probability of getting a positive if you have the disease, probability of positive given disease, equals 0.99, 99%. And that apostrophe is not. So the probability of testing positive given that you do not have the disease, we said was 5%, or 0.05. That's what we're told. I think you should have trouble thinking through the way of how do we apply this, or how do we apply this to this. And one useful way is to draw a tree like this and say, we start on the left, this is time, this direction, okay? So this is the starting point, we move to the right as things happen. We start by having two possibilities for any person. the probability that they have the disease and the probability that they don't have the disease, because that covers all possibilities. They either do or they do not have the disease. We know probability of having the disease for any person is 0.01. So, what is the probability of them not having the disease? Sorry? To agree with that, it has to be 1 minus, because these two must add up to 1. Either you have the disease or you don't. If that's the chance of having it, then 1 minus that must be the chance of not having it. Good so far. Phew. This is the toughest thing I ever have to teach. I live in terror of getting it wrong. Yeah, good. So we can fill in the whole table. A person either has the disease or they don't. After we reach this point where they either do or don't, we then have the test. And that gives us 2 more possibilities. They get a positive or a negative result. Let's take this chart, this line first. The probability of having the disease is that number. So that takes us to here. Then we can ask, what's the probability of them getting a positive result if they have the disease? And also, what's the probability of them not getting a positive result? Notice the apostrophe. Probability of positive, not positive, that is negative, if they have the disease. In both of these branches, we assume they have the disease, because that was how we got to here. We got to here because they have the disease. So we said, probability of disease is that number. Given that we've done that they have the disease, what's the probability of being positive, of getting a positive result if they have the disease? We know that already. That was in the setup. So we can write here 0.99. What's the probability of not getting a positive if you have the disease? Yeah, again, it's 1 minus the other probability. Yeah, it must be 0.01. It has to be 1 minus that, because either you got a positive or you didn't get a positive result in the test. So it's got to be that, so we derive that number from the setup. Following the other line, alternatively, you know the probability of not having the disease is 0.999. Then we take the test. Okay, so we assume they don't have the disease. What's the probability of a person who, so what's the probability of a positive test for a person who does not have the disease? It's in our setup. We're told it's 0.05. Therefore, what's the probability of not getting a positive if you don't have the disease? Yeah, it has to be 0.95. It has to be 1 minus this option. Probability of positive if you don't have the disease is 5%. Therefore, the probability of not getting a positive if you don't have the disease is 95%, which is 1 minus. Now we have all the information we need. We want to know what is the probability that you have the disease if we get a positive result. That's a really important question. Do we have the disease? We've got a positive test. Do we really have the disease? So that's what we want to know. And this will tell us how to work it out. Well, enough about deliberately list out one bit of information we'll have to calculate. Probability of A given B is the probability of B given A. So you just flip those two. You say the probability of positive given disease. And we have to multiply that by probability of A. A was probability of disease. So normally called our A is this, our B is pulse. So probability of B of this, yeah, times A, probability of disease, all over or being positive. Now we have one bit of information there we don't yet know. We know probability of P given this, probability of positive given this. We know probability of having the disease, the trial probability. It's that one, do this. We don't know the overall probability of getting a positive from any given test. Or we can find it out. Because there's only two ways to get to a positive test. That one, positive test, and that one. Agreed? They're the ones where we have positive test, positive test. Would somebody please with a calculator? Well, sorry, so first we'll say we multiply because we want this to be true and this to be true. So what's the probability here? What is the value of getting, what is the probability of getting to this point? Someone do that calculation, it's 0.01 multiplied by 0.99. Yeah. 0.1 multiplied by 0.99. What was the answer for me?
0.0000.
Should we all agree? So you call it out for me, 0.000. How many zeros?
3 zeros.
Yeah.
99.
Yeah, of course it is. That's it, but that's obvious. What about this one? It's going to be 0.999 multiplied by 0.05.
0.0499.
0 point, one at a time, digits, 0. Yeah.
4995.
Yep, you sure about that? Yep. And because we want to know, overall, what's the chance of anybody getting a positive test? We have to consider both possibilities. They got a positive test because they have the disease, or they got a positive test but they don't have the disease. So we add them together. The sum of those two. P pos is that one plus that one. Anybody care to work that one out for me?
0.05, 0.05,
Yeah.
0.94.
That looks right to me. Yeah, good. That's P pos. Now we have all the answers we need. We can say pos given disease 0.99. Is that right? Do stop me if you spot a mistake. I'm not infallible. Multiply by
0.001.
yeah.
That number there.
0.0594. Would someone do that for me? And I pray that this is the same answer I've got here. What is it?
0.1
I got
0
yeah.
dash.
I like to actually put it as a percent, but I'll do it both ways. Yeah. Give it to me as a decimal first.
0.019434629.
That's enough. Approximately equals as a percent.
Only 1 0.
There's a mistake, is it?
Yep.
Should be there?
Yep.
Yep. 2%. Under 2%. You almost certainly do not have the disease. Is that what you guessed from the setup before the who thought of it before I did the calculation? It was likely to be as low as that. Is that a surprising or an obvious number?
It's higher than I thought.
Higher than I thought.
Is it? Ah, because most I should have made you write down your guesses beforehand. Because most people, when they're here, I'll just remind you the setup. The test gives a positive in 99% of the cases where the patient has the disease. People hear that and think, I got a positive, I have the disease. But in fact, you almost certainly do not have the disease. I'm the 1 in 50 chance of disease. You can even, if you've got time to do it, you can even take a second test. Because, yeah, and you can just draw the table further and calculate. But this time, instead of the prior probability being this very low number, we say that the prior probability after one test is that number, 2% more that number, and you put that number back in, recalculate, supposing you take a second test and it's positive again. You've had 2 positive tests. I want to know, and this time I'm going to make you predict, what is the likelihood after 2 positive tests that you have the disease? And then you'd have to calculate it, but just to intuition, 2 positive tests. Remember, this test gives a positive in 99% of all cases where you have the disease. And you've tested twice and got positive. How scared are you? What do you think is the likelihood? You'd be very scared. I'd be terrified, yeah. Want to know what the number is? After 2 positive tests, you're still only 28% likely. 1 chance in 4. You're still more likely to not have the disease. Why? Why after 2 positive tests? What number in here is the one that's making all of our intuition go wrong? Yes, can you say it another way?
0.05 looks very small.
Yeah.
People who actually don't have the disease is a lot.
Yeah. Yeah. The people, exactly. The people who, almost everybody doesn't have the disease. The disease is very rare. Less, well, 1 in 1,000 people have it. And because that number is so low, even after 2 tests, you probably still don't have it because the test isn't perfect. Most doctors in my country get that wrong. They tell patients to be much more worried than they should be. I've got 2 options. I feel like I have used up as much of your brain power as I can, but we could do an application of this to a textual teacher's knowledge. So if you do an example, a textual example, an attribution case, I won't do all the maths. I think I'll just give you the setup and show you how you work it out. Because I want to give you a setup like this, but it's not a disease, it's a literary question. Now, that's why I wanted to get to, was to say we can use the same mathematics to ask the question, if we find a particular feature in some writing, and we know for different authors how likely they are to use that feature, can we figure out who wrote the text? That is, instead of a test for a disease, it's a test for authorship. Okay? So we need 3 writers, X, Y, and Z. That's their names. Okay? There are 3 authors. And they're each producing several 2,000-word blocks of writing every week. They keep writing the same amount, 2,000 words each, and after a year, they've produced a body of writing, and they haven't recorded who wrote which bit. We've just got a corpus text, a big digital file. All we know is that they don't work at exactly the same rate. They produce different amounts of that text. Of the body of writing, X has produced 20% of the text. It looks like about a fifth. Of the body of writing, Y has produced 30%. You hardly need me to tell you, therefore, Z has produced 50%. of the body of writing. So they produce different amounts of this collected work. They all use a literary feature we're going to call F. They all do something. It could be, and I'll show you this in a talk at, what time does the talk start today, Egypt?
4:30.
So I've got half an hour gap. Right, I must have work here. Okay, I want to give you plenty of time as well. Say the literary feature is, give me a simple example of some feature of writing you might look for. What's that? Agricultural. Yeah, they write in agriculture. That's what Shakespeare does and other people do. Yeah, or they use something called the feminine ending in verse. Or it could be that they use a particular word, an unusual word. We know how often they do it. Exactly, in the play, yeah. We know that X uses this feature F in 7% of all his writing. We know that Y uses it 11% in all his writing. And Z does this in 4% of all his writing. Those are their habits. And we can detect those habits. We can take a sample from this collective body of work and test for that habit. We can see if the sample features the phrase see a play or feminine ending or whatever. It doesn't matter what it is. It's anything that we can measure. So we take a 2,000 word block at random. We don't know where it came from. Well, we don't know which part of the text is by which person. That's just the overall total. We extract from the text 2,000 word sample. 2,000 word sample. And we find feature F in it. And we want to know, given that we found feature F, what is the likelihood that Z wrote that text? Can you see how it's an exact parallel to the biological text? Given the test, and given the prior probabilities, can we figure out the likelihood that Z is the author? Now, I call these prior probabilities because without F, without finding the feature, if we just extract it and chunk at random, we would say that just picking a piece at random from this distribution, the chance of X having written that sample would be 0.2, chance of Y 0.3, chance of Z 0.5. That is, the proportion of the overall body of writing that each person has written would be our expectation of their likelihood of having written it. I haven't got time to go through the whole, I wish I did. I don't want to take more than the next 15 minutes. I'll show you the notation. That's the setup. Prior probabilities then are probability for any text, any sample of your pardon. Prior probability, yeah, so we've got two. We've got three priors rather than two. Yeah. Those are what we call the prior. That is prior to our test, before we got the knowledge. The knowledge came from the test. What we're really getting to here is how much weight should you put upon the test? What's it telling you? The same way as in our medical example, we're saying, how should you change your mind because you took the test and got the results you did? But here we're saying, those are the prior probabilities if we know nothing about the feature. But how much should we change those if we find the feature in the writing? And Bayes will tell us. I won't have time to draw the tree. Maybe you can do without it. I'll take a leap of faith that we can go straight to applying Bayes. Probability of finding the feature F if X is the author. What do we give that number? Yeah, it's already on the board, 0.07. X uses F at that rate. So the probability of finding F if X is the author is that. Probability of finding the feature if Y is the author is 0.11. Someone stop me if I make any mistakes. So using this time of day. Yeah, 4. So I try to run 4. Good. Probability, one thing remember we needed to know was the probability of any test being positive. Here, we want to know the probability of finding F in any sample. The probability of finding F in any sample is the probability of finding F if X wrote it, plus the probability of finding F if Y wrote it, plus the probability of finding F if Z wrote it. So its probability of F is the probability of X being the author multiplied by the probability of finding F when X is the author. Yeah. Plus the probability that Y is the author times the probability of finding the feature if Y is the author. That's the same for Z. Probability Z is the author times probability of finding feature F when Z is the author. I've taken a step leave, I hope you're still with me. Probability of finding the feature, you tell me if this is what I've got on the board. Probability of finding the feature is the probability of X being the author multiplied by probability of finding F when X is the author. Times. Yep. That's one way to get an F. The other way is the probability of Y being the author multiplied by the probability of finding this feature when Y is the author. That's the second way of getting it. The last way is the probability of Z being the author multiplied by the probability of finding an F when Z is the author. I'm going to leap straight to that calculation. We can do that. You'll find all the terms there are given. It's 0.2 multiplied by 0.7. Yeah. Someone already got the answer here. Is that what you said? Thank you. Probability, that's probability of F. Phase to the rescue. Probability of A given B is the probability of B given A multiplied by probability of A all over probability of B. We need to apply that to our case. We want to know the probability that Z is the author given that we found feature F. We found F, obviously Z is the author. So that's going to be the probability of finding F when Z is the author times the probability of Z being the author, the prior, all over probability of finding F, which we just calculated up here. Anybody able to do that for us? I can write it out if it would help. I think it's
0.2.
to agree 0.04 times
0.5.
0.5, I agree.
Divided by 0.67.
Yeah, I agree. What does it come out as? 0.298. Can we agree 30%? Yep. Yeah. If you find F in the text, which you took as a sample, there's a 30% chance that Z is the author. even though Z, author, is the least likely person to use that feature. This is not enough to give you an answer. The likelihood that the author uses that feature won't tell you. The shares of the canon or corpus each person contributed won't on its own tell you the answer. But you can combine those two pieces of information and say that if you find feature F, the person least likely to use feature F is in fact, turns out to be most likely to have written the text, because in fact, simply because he wrote half the whole canon. That's what changes the outlook, that changes the probabilities. It's called Bayesian inference sometimes, but it's a way of saying, I've done a test. How should I change my knowledge? What does this knowledge do to my prior assumptions? And as with the medical test, you can run another test. And you can take these results as your prior expectation and run the same calculation again with a second test. It doesn't have to be the same feature, it can be another feature. That's one of the key ways that people these days do what we call authorship attribution, when you know, or you have a sense of the sample sizes, how much they wrote on the overall body of writing. You've got a sense of how often in the work that you do know they wrote. Remember, to know this, you must have some other writing where you know what Z does, you know what Y does, you know what X does, you know their habit. And then you can, from those two pieces of information, figure out the likelihood of a particular author. That seems like roughly 1 in 3. It's not very helpful, but when you run this with multiple tests of F, different kinds of F, ideally, completely different kinds of F. One based on word choice preferences, one based on poetical habits, one based on punctuation is another one. You could use sentence length, that's a feature. You could use word length, that's a feature. You could even use favorite letter. This person likes the letter B. Authors do differ, not only in their preferences for words, but for parts of words. 2 letters or 3 letters together. We can test almost anything that a machine can find as a digital string within a larger digital text. And we can combine them to get to never certainty, never complete certainty, but we can start changing these numbers and say, I think beyond reasonable doubt, we have proved that this person is the author. That's how we use this particular kind of statistics. It's a way of getting away from intuitions and grounding our work in the culture of statistics. Thank you for listening.
Okay, so thanks for the outstanding workshop today. So, can we have some questions?
Oh yes, if you like, yeah, I'll take questions, certainly.
Yeah, so we have a 10-minute left, so we are going to have the Q&A time. And if here is someone who have any question, please feel free to ask him.
Yes, do. But don't feel like you have to ask the question. I'm also happy to say that's what I have for you. Some people in this room probably know more than I do about some of this subject, so I may not know the answer to your question. I'll try. Yeah.
Yeah, what if we can extend these methods by not a one word or a phrase or multiple words, where we can find the text. How can we extend it?
Well, by the chaining process that I mentioned with the second biological test, we then use the outcome of the first as the prior expectation for the second. What we're really saying is, if this is true and this is true, what do I think now? What's my new expectation? And you simply repeat the cycle. It matters though that you get this right. It's quite easy to fool yourself about these numbers. It's quite easy to, you've really got to prove to yourself that that is what the author does. Language is weird. People writing is weird. I mean, it's a friend of mine said, made a quote I keep using, it's a wonderful quotation. He said that language is the ultimate big data. That is, it's the data set we least understand properly. It's more complex than most of the big data sets we have, and we're still learning all about it. And the same kind of surprise we had in the first half of the class when two people shared a birthday, the same kind of surprises keep coming up in language. Just before we get to your question, Brian Vickers is a practitioner of this kind of work, who in my opinion is very poor at this work, very bad at it. And his method, I'll describe it briefly. He takes a text that he knows who wrote it, and a text that he wants to attribute. We don't know who wrote it. He looks at the two texts and he uses what we call plagiarism detection software. And it finds phrases in common. So it finds all the phrases that are shared, all the 2, 3, or 4 word phrases shared by the two texts. Then he searches for what are the most common phrases in English. And he throws all those out. He takes them out of his list. He wants to find just the rare, unusual, uncommon phrases that are shared by the two texts. The one he knows who wrote it, and the one he's trying to attribute. And he ends up with maybe, in a large text, maybe a play, he ends up with maybe 10 or 20 rare phrases that other people don't use, but these two texts share. And he says, behold, it is proven I have done it. It sounds convincing. It's not. It shouldn't be. Any two large texts, any two, will have in common, will share rare phrases. To prove this point, there's a friend of mine, Matt Stegley, at the University of Bristol, who did his PhD the same time as I did, on a different subject. Both PhDs are 80,000 words. I have the text of his, I have the text of mine. I did Brian Vickers' methodology. I found all the phrases in common. I've removed all the phrases that are common in English, so all the phrases the two texts shared. I took all the phrases that, of that list, I then removed all the ones that are frequently found in English, to leave behind 15 unusual, rare phrases that Matthew Stengel and I both happened to use in our PhD thesis. By chance. According to Vickers, either I wrote Matthew's PhD or he wrote mine. Neither is true. Large texts just have weird things in common, just as even moderately sized groups of people have weird things like shared birthdays in common. Thanks for the question. Do you have a question?
My question was tangentially related to that answer. Like, for example, let's say in like genres, for example, there are commonalities in the way people structure words and phrases.
Yeah.
And even if the two authors use the same like feature, and they have a different probability of those features coming up, how are you going to model it? Like, how are you sure that the genre is going to model it up?
Yeah, great question. Yeah. And what you're really talking about now are what we sometimes call confounding variables. Things that look like they make a difference, but in fact they're messing with your values, your judgments. Let me give you a concrete example. We sometimes find in a play that we're trying to attribute, we're trying to find out who wrote it. And I work on only plays. I don't work on poetry or anything else, so it's always playing when I say text. We have plays with unusual features. And this particular example had a whole plot line that was clearly dependent or similar to the plot of another play. But whereas it was a minor feature in that other play, and we know who wrote that other play, in this play it was the main structuring feature, it was the dominant theme. And an argument that was made by a respected scholar and widely agreed with was that one text had the plot fully worked out and in detail, and it was a large part of the whole meaning. The other one, it was merely part of one scene. Here was the argument. You wouldn't write a whole play based upon what you found in one part of one scene in one other play. more likely the play that had the small version had written that small version because it drew upon the one that had the full version. In other words, there was an arrow, directionality. And that sounds convincing. Who would take a small feature of one text and expand it to be the governing theme of their whole play? But I thought, there's a great novel by Martin Amis called Time's Hour, 20th century novel. Maybe you know it, it's a wonderful play. It's a story in which a man lives his entire life backwards. Everything happens chronologically backwards. So he finds that there are some strange things happening in life, like taxi cabs arrive instantly, but you have to wave them goodbye for a long time. You get it? The hailing of a cab, before you get into it, and then leave, gets reversed so that the cab arrives instantly, but you have to spend a long time saying goodbye to the cab. He lives his whole life backwards. Martin Amis got this idea from one paragraph in the novel Slaughterhouse 5 by Kurt Vonnegut, where a man watches television, I think, and everything for some reason happens backwards. So it is possible for someone creative to take a small part of one larger work and expand that little part into the whole of their structure. You can't assume anything. So I think I've come a long way from your point, but it's that be very careful about what you think, but in general, be very careful about what you think is inherently implausible, because inherently implausible things do happen. As David Brown showed in the video on the start, 10 heads in a row will happen if you wait long enough. And if you think how many novels have been written, some strange things are bound to happen somewhere between any two novels, if you're willing to wait for them. Yes. Any more questions? Oh, sorry, go back to the part.
With the F order, the future word means the long-term word or...
Yeah, it can be any text. F just means a feature of the writing. It can be any feature that you can catch.
It can be a verb or...
It could be a choice. It could be anything. It could be a particular kind of metaphor. It could be a particular kind of verse style. It could be a way of organizing paragraphs in a novel. F just stands for feature. Any verb, any feature of the writing you can measure is it. It could be, there's a writer, a man who worked, I'll talk about this a little bit in my talk 4:30, but there's a man whose job was to write out plays. He didn't compose, he didn't think them up, he simply had the job we call scrivener, copy plays. And he had a feature of his writing. He would just put certain words C-A-T, the small cat, he put them in brackets. It's an unusual feature. Those of us who work on it, it's called Valve Trade. We sometimes call this, in my field, SWIBs. Single word, brackets. There's no good reason for it, other people don't do it, but Valve Crane does it. So anything you can measure. So you can count how often do you find a single word in brackets in a text, that's a feature. So anything will do as F, as long as it's countable, and you can demonstrate prevalence. Thanks. Any more?
Any more questions? All right.
Okay.
So, unfortunately, our time is up. So let us conclude this session here. So as we already know, we have more presentation right after this workshop. So hopefully, let's all group together go to the 이문한국 진로. Thank you for
Cool, yeah. Thank you. So, about this, you might 확실히 보이셨네. 확실히 보이셨네.
Okay.